So the second type of plate boundary that we'll look at are convergent plate boundaries. Con means come together, and verge means move. So they're coming together, moving towards each other. So in this case, the different plates move towards each other, and by doing so, sometimes they collide, and typically one will get overridden by the other, hence destroying that plate's crust, the one that's being overridden. So this is the motion, let's see, that goes on in this specific type of plate boundary. So again, divergent plate boundaries create crust, convergent plate boundaries destroy crust. So the parts that tend to get destroyed are usually older oceanic lithosphere, if there is oceanic plates being involved within this particular boundary. So the one that is further from the spreading center is typically the one that is being destroyed in this case. So about 40% of all plate boundaries on Earth are of this kind as well. So 40% were divergent plate boundaries, 40% convergent plate boundaries, which leave about 20% to be the transform plate boundary, which we'll look at later on. So during convergent plate boundaries, the leading edge of one of the two plates in contact is bent downwards as it slides beneath the other plate. The lithosphere of the denser plate will typically descend and is subducted into the mantle, and the less dense plate, the more buoyant one, will sort of sit over the other's plate leading edge at a certain angle, depending on the density difference between them. So this angle at which the leading edge of the subducted plate has as it plunges into the mantle will be greater if that plate's density is much greater than the plate that is overriding it. So the angle at which the leading plate of the subducted plate has as it plunges into the mantle will also be lower if that plate's density is close to the density of the overriding plate. So again, assume, let's have this idea. If two plates are coming together, let's put a real world example, the Nazca plate and the South American plate that you're seeing in this image, for example. Let's assume, and I think I'm not too crazy by saying this, that the Nazca plate is much denser than the South American plate. In that case, the angle at which the Nazca plate is plunging into the mantle is going to be much greater because the density difference between the two plates is very great. However, if, let's try to find another example. For example, the Cocos plate that is being subducted underneath the North American plate up to the north, if the density of the Cocos plate is not much greater than that of the North American plate, then the angle at which the Cocos plate is plunging into the mantle is not as great. Okay? So because of this, the process related to this type of boundaries is the process of subduction of one of the two plates. That's how we call it, subduction of one of the two. So many times the convergent plate boundaries themselves, we call them subduction zones. So typically, with this type of boundary, a feature called a deep ocean trench is formed. Not all of the convergent plate boundaries have this type of feature formed, however. Only those where oceanic lithosphere is involved. And this feature is typically a long linear depression in the seafloor that is generally located a few hundred kilometers offshore of either a continent, such as the Peru-Chile Trench, or a chain of volcanic islands, such as the Aleutian Islands up in Alaska. So again, if we look at this map, about here is where the oceanic, deep ocean trench, lies for the Peru-Chile Trench, and up here is where the Aleutian Trench is located. So this feature occurs again where the oceanic lithosphere bends as it's descending into the mantle along that subduction zone. So you can see that specific feature in this red circles, the trench being right here. And you see that in these three different cases, the angle at which the plate that is being subducted varies. And that depends on the type of convergent plate boundary that is in fact taking place, and we'll go over that in the next few slides. So as I was saying, there are different types of convergent plate boundaries, and that's going to vary depending on whether the two plates that are coming into contact are of continental nature or oceanic nature, or both, depending. So the first type of convergent plate boundary is the oceanic continental convergence. Okay, so that's the first one that we're going to look at. The other two are going to be the oceanic convergence and the continental convergence. So the first one again is the oceanic continental lithosphere convergence that we have. In this case, the oceanic lithosphere will subduct as it is denser than the continental lithosphere. As the leading edge of the subducted plate descends, it eventually melts, basically. Not quite melts, but slowly dissolves, if you would. And it becomes part of the asthenosphere. As this occurs, some of the asthenosphere material that surrounds the descending plate will melt as well, meaning it becomes less dense, and it will want to rise upwards, ascend upwards, because it's more buoyant now. This melting occurs because the lithospheric plate that is subducting is wet, is full of water incorporated within the rock, water that incorporated within the rock at formation, or later on with different deformation that it may have seen. And this wet rock in a high pressure environment will melt at substantially lower temperatures than does dry rock of the same composition. So assume you have let's just say a sandstone. If that sandstone is wet, it will tend to melt at a much lower temperature than it would if it was completely dry. Okay, that's the idea. So the material that rises upward by the melting and consequent density decrease will either ascend all the way to the surface, causing volcanism, but more often than not, it will be cool enough before it reaches the surface, and it will simply contribute to the thickening of the crust. So we'll look at this type of igneous activity when we cover Chapter 4 on igneous rocks. So because of the rising of the more buoyant material, it is common that you will have volcanic arcs associated with this type of convergent plate boundary, with this oceanic continental convergence. And these volcanic arcs are linear volcanic mountain systems that are parallel to the edge of the subducting plate. Okay? So two very good examples of this is in the world are the Cascade Mountains in the western US and Canada. So as can be seen in the diagram on your screen, along with Mount Rainier as one of the volcanoes from this volcanic arc in the picture there. This volcanic arc is caused by the subduction of the Juan de Fuca plate underneath the North American plate. So you're seeing Juan de Fuca plate right here being subducted underneath the North American plate. And because of this subduction and the different processes that are going on here, this Juan de Fuca plate slab kind of melting again because of the water that was in there, and the asthenosphere rising, or parts of the asthenosphere material rising upwards, where is it? Creating this volcanism is why we have this volcanic arc in the continent, which causes the cascades as we know them today. Cool. Another good example are the Andes Mountains in South America, which are caused by the steep subduction of the Nazca plate underneath the South American plate, as I gave you in the example from the last slide. So the Nazca plate right here is being subducted underneath the South American plate at a very steep angle, which is causing very high amounts of seismic activity, for example, and also volcanism that is undergoing here all along the Andes Mountains. So the second type of convergent plate boundary is the oceanic convergence. Just like in the convergence of oceanic continental plates, the denser plate will subduct underneath the lesser dense plate. And just like in the other case, the melting at depth causes rising of material upward, sometimes reaching the surface as volcanisms, sometimes not quite all the way to the surface. So in this type of convergence, the feature that is formed typically is a volcanic island arc. And it is also a linear chain of volcanoes that parallel the subduction zone. So it's very similar to the one we saw in the previous example, except that in this case, it's an island arc because there is no continental landmass to sustain this volcanic events or features, I should say. So a great example of this is the Aleutian Island arc in Alaska, as the Pacific plate is getting subducted underneath the North American plate. But other examples are, for example, the Mariana Island arc and the Tonga Islands as well in the Pacific. So because we have the Aleutian Islands in this example, I just wanted to point out in this image the pretty clear deep ocean trench that is just underneath it, again parallel to the subduction of that Pacific plate. And right after, if you can imagine the Pacific plate subducting underneath the North American plate, going towards, I guess, the north in this case, and then melt rising upwards and causing these volcanic features all along the margin as well. So the last type of convergent plate boundaries is when you have continental convergence of these lithospheric plates. And just like in all of the convergence of plates, the denser plate will subduct underneath the lesser dense plate. The oceanic material that may have preceded the landmass tends to sink and subduct relatively easily, just like you're seeing here in the image. So, for example, this Indian or Australian Indian plate initially had some oceanic lithosphere attached to it, and it subducted relatively easily underneath the Eurasian plate. But once continental lithosphere got involved in this motion, it did not happen so easily because both of the lithospheric plates are now nearly equal in density. So the subduction of one of them is not as easy as it used to be with just oceanic lithosphere being subducted. So, however, once the landmass margin, actually encounters, as I said, another landmass, both of the continent's material are relatively buoyant and won't cede to subduction that easily. So they merely kind of float. So you get this large amount of deformation of the rocks at either plate's margin, which, it causes material to build up of sedimentary and also now metamorphic rocks, which are rocks that have been greatly deformed by pressure and temperature, also accumulate. And in some cases, some oceanic lithosphere may become incorporated in the mix of that sedimentary and metamorphic rock as well. So if you can see right here in this diagram, this is part of the oceanic lithosphere that got incorporated within the sedimentary and metamorphic rocks as part of the idea. So in this case of convergence, unlike the last two, you get very little melting, so you don't have very much volcanism taking place because you don't have a whole lot of subduction taking place either. So these rocks that are the result of this type of convergence end up building up into a new mountain belt, as are the Himalayas right now, for example, which are still growing thanks to the continental convergence of the Eurasian plate in the north and the Australian plate in the south. So older mountain belts, such as the Alps, the Appalachians, and the Ural Mountains, have all formed due to this type of collision, which was a convergence of continental landmasses. But in this case, these formed many million of years ago due to previous plate motions that were in place at the time of their formation.